Hello everybody and welcome back to another visual pattern challenge. Here's our pattern today. Here's step 1, here's step 2, here's step 3, and your challenge is to predict the number of squares in step 4. If you can do that, can you predict the number in step 43? And can you write an equation that could be used to predict the number of squares in any step at all? So that's the challenge today. If you'd like to accept it, pause the video and see how far you can get. All right, so let's just gain some visual understanding of this first. And I guess, mostly this is rectangles that are growing in size. That leads me to think this is going to be a quadratic and not a linear pattern. And then there's this center square missing. It looks like it's always just one missing. So that might just be a -1. So I guess if I were going to predict step 4, I'd want to find the pattern of the sides of the rectangle and then subtract 1. Let's see, it looks like we have 2, 3, 4. So I guess this side on the next rectangle would be 5. And then we have 5, 7, 9. 5, 7, 9. So the next one would be 11. Looks like it's going up by 2. And then we're going to have this one missing, so that's going to be our -1. So 55 times 11, sorry, 5 times 11 is 55, -1 should be 54. So I'm going to predict 54 squares in step number 4. Okay, now I think it makes sense to sort of arrange these numbers, look at these numbers in the same way we've been doing here. This is a 2 by 5 rectangle -1. So actually, let me make a little chart here. We'll have the step number and the number of squares, but I'm going to write these out in the form of this sort of equation that I've been using to calculate here. So in step 1, I'm going to write this as 2 times 5 minus 1, and that is 9. And in step 2, this is 3 times 7 minus 1, and that would be 20. And in 3, this is 4 times 9 minus 1, that'd be 35. And in step 4, we're saying it's going to be 5 times 11 minus 1, and we calculated that to be 54. So let's take a moment to verify that this is a quadratic pattern by taking the differences here. So 20 minus 9, that is 11. And 35 minus 20 is 15. And 54 minus 35 is 19. So we're not getting a constant in the first set of differences, so that's not a linear pattern. If we take the second set of differences, 15 minus 11 is 4, and 19 minus 15 is 4, that's where we're getting a constant. So we know this is quadratic, and actually this number you get for the difference, if you divide it by 2, that's the coefficient of your leading term of your quadratic, of your x squared. So in this case, we're going to have a 2x squared in here somewhere. Now, at this point, to try to find an equation and then use that to get step 43, you could go in a couple of different directions. You could look for the 2x squared in every step and sketch that out and then see what else is going on. I think we have an equation right here in this chart of numbers. We just have to figure out what this number is in relation to the step number and what this number is in relation to the step number. Now the first one, the width of our rectangle, it's fairly easy. In step 1 it's 2, in step 2 it's 3, in step 3 it's 4. So it's always one more than the step number. So our width, and what I'm going to do is make an equation that says the width times the length minus that one square that's missing. So that's what I'm working on here. And our width is the step number plus 1. So that's the width. We've got the width done. The length is a little harder. It's 5 in step 1, and then 7 in step 2, and 9 in step 3. It goes up by 2 every time. If we were to take the difference between each of the lengths, you'd get 2. What that means is it's going to be 2 times the step number and then plus something, right? So 2 times 1 would be 3. To get to 5, we'd need 2 more. So I think it's going to be 2x plus 2. Sorry, 2x plus 3. We'd need 3 more. 2 times 1 is 2, plus 3 is 5. So 2x plus 3. Does that work in step 2? Step 2 would be 2 times 2. That's 4 plus 3. That'd give us 7. Yeah. And in step 3, 2 times 3 is 9 plus 3 is 2 times 3 is 6 plus 3 is 9. That does give us the length in step 3. Okay, so length 2x plus 3, width x plus 1, and then I've just got this minus 1 that I shouldn't forget. You could leave this equation just like this. That's fine. It's perfectly adequate. I think it expresses what we see visually here. I'm going to go ahead and FOIL it out, though, and simplify it. So let's see. That would be 2x squared. So these two, 2x squared. And then 2x times 1 is 2x. X times 3 is 3x. So that adds up to 5x. And then 1 times 3 is 3. But then minus 1 would be 2. So I'm getting 2x squared plus 5x plus 2 for our equation. Let's just test quickly if that works. So 2 times 1 squared plus 5 times 1 plus 2. Well, that would be 2 plus 5 plus 2. That would be 9. Yep, that's how many we get in step 1. What about step 2? That'd be 2 times 2 squared plus 5 times 2 plus 2. And 2 squared is 4 times 2 is 8, so that'd be 8 plus, and 5 times 2 is 10, plus 2, that adds up to 20. Yeah, that's what we're getting. You can go ahead and test this with step 3 and step 4 if you want to, but I'm pretty sure this is our equation. So y equals 2x squared plus 5x plus 2. Now to calculate the number in step 43, we're just going to plug 43 in for x there. So this would be 2 times 43 squared plus 5 times 43 plus 2. Well, running out of room here. I'm going to go down here. So 43 squared is 1849. And 5 times 43, that'd be 215. And then our plus 2. Let's see, 1849, we want to double that. That's 3698. And then plus 217. That should give us 3915. So I think there are 3,915 squares in step 43. What do you think? Do you agree? Did you get 54 for step 4? How about an equation? Were you able to arrive at one? I'd love to know. Let me know, guys. Thanks, everybody.